Why are your summer electricity bills through the roof and winter electricity bills much lesser? Why do parents rage when you forget to turn the AC off, but do not so much mind if you leave a light bulb on in another room? That's because different devices use different amounts of electrical energy when used for different durations of time. Electric devices have power ratings to indicate their energy consumption. Let's learn about electric power in detail. The energy rating of electrical appliances like televisions, air conditioners, washing machines, etc., has made it easy for consumers to purchase cost-effective products. These star ratings not only indicate the energy efficiency of these appliances, but also help us to reduce our electricity bill. One of the factors that govern these specifications is electric power. Let's discuss electric power and power dissipation. Here's a resistor connected in series to a battery. The positive terminal of the battery is connected to end A of the resistor, which is at higher potential, VA. End B is at lower potential, VB, as it is connected to the negative terminal of the battery. Let V be the potential difference between ends A and B of the resistor. A steady current I is produced in the circuit directed from end A to end B. Thus, the amount of charge that moves between the two ends of the resistor in time delta T is given by delta Q is equal to I delta T. Say that the charge possesses electrical potential energy U1. This charge, delta Q, while moving through the resistor, collides with the molecules of the resistor and transfers some energy to the molecules. Due to this, the electrical potential energy of the charge decreases, and let's say that it is equal to U2. The decrease in electrical potential energy delta U is equal to delta QV. Substituting the values we get, delta U is equal to I delta TV. Since the charge moves through the resistor with constant drift speed, the average kinetic energy remains constant while the potential energy decreases. By the law of conservation of energy, the decrease in electrical potential energy should be accompanied with a transfer of energy to some other form. In this case, the loss in electric potential energy appears as the heat energy of the resistor, and consequently it gets heated up. The rate of transfer of electrical potential energy is called electric power. It can be calculated as delta U upon delta T, which is given as P is equal to IV. The SI unit of power is joules per second, also known as watt. Higher unit is a kilowatt. Now say that the resistor has resistance R ohms, then the energy lost in the form of heat energy is called power dissipation. Now by using Ohm's law, V is equal to IR. Equation 1. On substituting in equation 1, we get the equation of power in terms of current. It is given as P is equal to I square times R. Again, to derive the equation of power in terms of potential difference, substitute I is equal to V by R in equation 1. We get P is equal to V square by R. These two equations of power are applied to transfer of electrical potential energy to heat energy in a device with resistance like a room heater, iron, etc. From these equations, we can infer that for a fixed potential difference V, when resistance decreases, power dissipation increases. This also holds true because as resistance decreases, more current flows through the circuit. Thus, we conclude from P is equal to IV that for a fixed potential difference, loss of power is directly proportional to current. We've observed that all electrical appliances like televisions, air conditioners, washing machines, etc., are given a power rating that usually states the maximum power that is consumed by the device. Power tells us how much energy a device uses per unit time. A washing machine with a power specification of 600 watts, when operated for a period of 30 minutes, that is 1800 seconds, will consume 1080 kilojoules of energy. However, since electrical devices use large amounts of energy, energy consumed is often expressed in kilowatt hours. The kilowatt hour is a measure of electrical energy equivalent to the power consumption of 1000 watts for 1 hour. Since 1 hour is equal to 3600 seconds, 1 kilowatt hour, when expressed in joules, is equal to 3.6 times 10 to the power 6 joules of energy. Thus, if the washing machine of power rating of 600 watts is operated for 90 minutes, that is 5,400 seconds, the energy consumed in kilowatt hour is calculated as 0.9 kilowatt hours. Based on these energy consumptions, electrical appliances are given Energy Star ratings. The appliances which consume less energy are given high energy stars and are considered to be cost-effective. To summarize, the rate of transfer of electrical energy is called electric power. The SI unit of power is joules per second, also known as a watt. Higher unit is a kilowatt. Electrical power is given as P is equal to IV. The two equations P is equal to I square R or P is equal to V square by R are applied to the transfer of electrical potential energy to heat energy in a device with resistance. Electrical devices use large amounts of energy, and hence energy consumed is often expressed in kilowatt hour. The kilowatt hour is a measure of electrical energy equivalent to the power consumption of 1000 watts for 1 hour. The appliances which consume less energy are given high energy stars and are considered to be cost-effective. We discussed the fundamentals of electric current, but at the same time, we are left with so many questions, like, from where does electricity in our homes come? Is there a huge battery somewhere? What are all those electrical poles and transformers and wires with high voltage and danger signs? We will discuss everything as we move ahead. Stay tuned.
Keep imbibing. We believe in you.